Okay, video on electrostatics here. This is going to be, I don't know how long, to be honest with you. But this topic we had kind of started in, school. No, I don't believe we did actually, did we? We did a bunch of simulation labs with this. So I just paused it for a second just to go double check the topics we had actually done. And I really want you to focus on the conceptual with this. We're gonna talk mostly about the attraction and charging, repulsion, and Coulomb's law. Electric field and voltage stuff is very important. However, I just don't feel too comfortable with getting to those equations too much. The electric field equation is pretty easy, but voltage is a very notoriously abstract concept for physics in general until you really kind of understand what's going on. So this brings us into the new topic 4, which again, I gotta post solutions to topic 3 and topic 4, the answer key to the review book. I can post that for you. I just gotta find a minute here. Things weren't crazy enough with everything. And then my mom goes to the hospital, which thank God she's okay, but just adds another wrinkle into the formula. But anyhow, so the big thing is positive, negatives, conductors, insulators. So this concept of charge. What is charge? Well, charge is technically not a thing. It's a property of matter, right? So good old electron, right? Little old electron. What does it look like? I don't know. Probably a little raisin or something. Who knows? Its mass, 9.11 times 10 to the negative 31 kilograms. I should probably double check that. I haven't written that in quite a while. So handy dandy reference table. Rest mass of an electron. Oh yeah, okay. Some things just stick. What's the charge of an electron? Well, the symbol we use for charge is a Q, a lowercase q. Now, there's actually 2 ways to represent the charge of an electron. Negative 1e, where e is the fundamental charge unit, just assigns 1 unit of charge to an electron and a proton, or 1.6 times 10 to the minus 19th coulombs, which is technically the scientific base unit for the charge of anything, for charge, I should say. So again, charging isn't a thing. The thing is the electron. All right, and it has mass and it has charge. It has this property of mass and property of charge. And what are those anyway? Well, those properties dictate how the electron will behave in different physical situations. That's the whole point of physics, right? Is being able to find equations and observations and use math to be able to predict how physical systems are going to behave based on its properties. So, and then what's cool about that is once you can fully predict how systems are going to behave, you can start to think of systems that don't exist at all and draw them or simulate them, 3D model them, and you can predict how they're going to behave to a very high degree based on the physics, which is really cool. Look at, video games, right? To first-person shooters, they run on physics engines, right? We can use the physics engines to, if I go forward, this is where this person's going to move. If I jump off this ledge, this is how I'm going to fall. Now, video games, some of you probably know that the physics engines are typically not gravity-based. They're typically like ultra exaggerated in terms of the accelerations. They're actually video games that have been modeled real physics gravity. They're actually kind of boring because you can't move as fast and jump as quickly as you think. But anyway, so that charge. The opposite of the electron is a proton, which, what does that look like? Well, I don't know. Something bigger than an electron. Maybe it's a orange or something. I don't know. So proton has a mass of 1.67 times 10 to the negative 27th kilograms, which is like, okay, it was 9.11 times 10 to the negative 31. So it's almost 10 to the negative 31. So that's like negative 30 or so, the electron. So this is 4 orders of magnitude. The proton is 4 orders of magnitude bigger than the electron, right? So this is 30, 27, or 3 orders of magnitude, I suppose. So it's like a good 1,000 times more massive, you know, the proton, over 1,000 times more massive than the electron, which, you know, which helps us to predict how a proton will behave as compared to an electron when released in an electric field or when streaming through Earth's magnetic field. You know, the electron is bent in its path more quickly because its mass is less. The charge of an electron is simply plus 1 e, or positive 1.6 times 10 to the negative 19th coulombs, right? So there we go. Proton, electron. So when we charge an object, for instance, if you rub a balloon on your hair, I use one of my daughters as an example. They have this blonde hair. All right. When you rub a balloon on your hair, what happens is the balloon takes electrons off of the hair. I think. Is that what voltage did? I don't know. It takes electrons off of the hair. So literally, electrons, because the balloon is higher on what's called the triboelectric series. It's kind of like electronegativity difference. The latex rubber that makes up that balloon attracts electrons to its molecular structure more than the hair attracts its electrons. So it actually can, when they're put next to each other, the rubber balloon actually pulls on the valence electrons of the hair more than the hair itself pulls on those valence electrons, so it actually takes them. That's how things get charged. The two objects touch or get very close to each other, and whatever one pulls on the electrons more, think of a tug of war, it'll take some of them. All right? It doesn't take all of the electrons from the hair, but it takes some of the free, I shouldn't say free, but some of the valence electrons that aren't strongly bonded to the structure, molecular structure. So that means if I take electrons away from the hair, that means I leave the hair positively charged. So if I take 10 electrons off the hair, which is absurd, you never take just 10 electrons. We're talking like trillions and trillions and trillions of electrons get transferred. The hair gets left positive. So for every 1 electron that gets transferred over, you leave behind 1 positive charge, 1 proton that stays behind. Protons are stuck, right? Protons, we don't move from one place to another. You can't take a proton, right? If we have an atom made up of protons and neutrons, let's say the black ones are the protons, right? I don't know. I'm just drawing this. If I can't move protons out of the nucleus, right? They're stuck together with something called the nuclear strong force. And in fact, if I was to take a proton out of the nucleus, that is a nuclear reaction. That is fission, right? Because you are changing this. If this was, helium, and I took a proton and now it's hydrogen, you are physically changing the structure of the nucleus. It's a nuclear reaction. That's fission. So that doesn't happen when we rub a balloon on our hair. Protons can't move from one thing to another in these everyday electrostatic experiments. So the drawing in the book is this comb thing. One of the important things to learn is, okay, so that's how things get charged. Electrons move over, right? So then you take that balloon now, it's charged up negatively on the surface. The balloon is an insulator. An insulator versus conductor. All right. On an insulator, charge cannot move across its surface. So if I put electrons on that balloon, they stay where you put them until you take them off. if I put charge on something metal or a conductor, that charge will distribute. It'll like, almost like, I'm trying to think of when you ever put like dye in milk, it like spreads out, like diffusion. That's basically what happens with the electrons when you put them on a, something metal, right? They spread out across the surface. It's like dropping a bunch of little things onto an air hockey table. They bounce off and they're going to spread out and get as far away from each other as possible. And, you know, they just don't go to the outside edge either. Because if they all went to the outside edge, they'd all be grouped together and they'd repel away from each other. So it distributes itself on a conductor, not the balloon. On a conductor, the charge distributes itself evenly across the surface. It can accumulate in certain areas depending on the physical structure of the surface. And if it was a perfect sphere, the charge would perfectly distribute itself across the surface, which is kind of cool. So the wall hanging out over here, this is the old thing. The wall is neutral, right? But it's also an insulator, and it's neutral. So what happens is when you bring the balloon towards the wall, what happens is something called polarization. Initially, the molecules are all just kind of randomly distributed, right? Like pretend these are the molecules that make up the wall, right? They're randomly distributed to start off with. I drew them polarized already here, which is not good. But what happens here is the electrons that make up these molecules, as you bring the balloon close to the wall, those electrons are in these molecules. They want to get away from this balloon. They get repelled from the electrons on this balloon. So the electrons on the wall get repelled away, which leaves the surface of the wall essentially positive. And those positive charges pull on the electrons. And they pull on the electrons more than the electrons are repelled by the electrons in the wall because they're closer. The closer two charged objects are together, the greater the force. All right? Let's talk about conductors for a second really quick. Just to kind of review. Again, I'm not going to get too much into voltage and electric field. I'm sure that some of you are putting those questions into the review assignment. That's okay. It's good to know about that, but I really don't expect too much out of you in this unit or the next, really. I'm going to keep it very, very basic. You know, conceptual, positive and negative. One important thing to remember is, well, let's talk about conductors for a second. So, a conductor is metal, right? If you have two conductors, right, they will attract. They will attract. Like if I have a positive conductor over here and something neutral over here. So neutral, let's say there's no excess charge. So any charged object will attract to any neutral object because of polarization. So what happens here is this positively charged sphere metal sphere, let's say, like think about the top of the Van de Graaff generator, which you guys it's not even relevant because you guys never saw it. The positively charged sphere, when you bring it near this, it is going to attract electrons in the metal to the surface, which polarizes the metal sphere. Now, what's different than the wall here is that the electrons can move much farther across the surface. You know, remember, in an insulator, the electrons can't move across the surface. In the conductor, the electrons can move across the surface, and here they are. They get pulled, you know, they're going to get pulled up here. You're probably going to get a pretty good accumulation kind of in this zone right here, right? Because these positive charges are pulling on these electrons. These will attract. Now, when they touch, what's cool is when they physically touch, you actually get a nice transfer of charge, right? So some of these electrons go onto this surface. I should have made squares. All right, they touch. What happens is you get an accumulation of charge over on this guy. So if there were 12 positive charges over here, excess charges over here, you're going to get essentially 6 electrons are going to come over here, leaving this one 6 over here. So if it was 12 to start off with total, when you touch them and separate them, now they're both going to have 6. All right, so conductors, when you touch them together, they'll share the charge that is accumulated on one of them and split it, divide it up. The last thing I just want to quick talk about is the actual mathematical equation for the attraction and repulsion of charged objects. And the reason I want to talk about this one quick, because it is pretty important, because it follows the same form as the gravitational force of attraction only. So gravity is only attractive, which is kind of interesting, because why should it only be attractive? I mean, I don't know the answer to that. I'm sure there's a good reason for that, but if charge can be attractive and repulsive, you'd think that there would be some way that gravity could also be attractive and repulsive. And same thing for the nuclear force, but who knows? There must be a good physical reason for that, or it's simply a mystery. Anyway, Fe, K, Q1, Q2 over R squared. K is the electrostatic constant. 9 times 10 to the 9th newtons times meter squared per coulomb squared. This is only in air or a vacuum, the electrostatic constant. Unlike gravity, which is just universal, the electrostatic constant that we use is only good in air or a vacuum. It turns out that constant can change depending on the material separating the charge, which is super important in a lot of situations. A very useful thing. So certain nylons and plastics and polymers, they slow down, so to speak, the electric field. All right, they don't polarize very well. You have to transmit the field through them via polarization, essentially, and that kind of slows down the force of attraction, which is kind of interesting. KQ1, I'd be interested to see if we took the two Van de Graaff and we had two pith balls and we put a piece, if we could find a material we could put between them, if we'd see the force decrease. I bet we would. All right, charge of one object, charge of the other object. R is the distance between them. All right, so let me make a drawing to go with this. Let's say we have two charged objects, certain number of coulombs here, that's a Q, not an A, certain number of coulombs there. R is the distance between them. And I encourage you to go back and look at the review topic on this. There's some good calculations there. We had some homework assignments on that worksheet, I think. Yeah, so I think there's some good solutions for those worksheets showing a lot of Coulomb law. Oh yeah, there's tons of solutions on it for Coulomb's law. Pretty much Unit 8 worksheet 1 is where we're going to end this unit with this type of stuff. So I'm not going to do a numeric one right now. Just make sure this is in meters and this is in coulombs. Oh, one of the things I should point out, actually, now that I'm thinking about it, this video's getting a little longer than I intended, but oh well. The units for charge, sometimes we have these prefixes: microcoulombs, 15 nanocoulombs, 12 picocoulombs. So micro is 10 times 10 to the negative 6 coulombs. So basically, your prefix is that number right there. 15 times 10 to the negative 9th. Now I should probably make it actually 1 point, something, so I'm not doing it wrong there. 1.2 pico is 10 to the negative 12th coulombs. All right, and this is the range of charges that we're talking about, right? Like when you charge that balloon up, you're probably actually like in the femtocoulombs. It's an F, a lowercase f, which is 10 to the negative 15th coulombs, right? It doesn't take much charge in terms of the amount of coulombs to have a really big effect. All right, so watch out for that. That's one of the very important things about this unit, actually. We use this unit to practice these prefixes quite a bit. So take a look at the homework solutions that we had already done. Blue book solutions, I'll take this upstairs right now, and I'll take the answer key upstairs right now and make a PDF and get it posted. I'll post it right on the main page for Physics 11H, all right? Watch this in high speed. Sorry, got a little long. Love y'all.